All right, so let us introduce the wave. Now, when I say wave, I'm talking about anything that has a wave shape or function. So this can be everything from the ocean wave. This can be a wave in a jump rope. This can be a sound wave, a light wave, an electron in his wave form. Doesn't matter. A wave is a wave is a wave. But in general, this is the shape we generally associate with a wave, quote unquote. And it's got several pieces that we need to talk about. First off, the very top of a wave, in any form, ocean wave, jump rope wave, electron wave, the very top is called the crest. Occasionally you'll see it called a peak, but that's less likely. More often it's called a crest. The very bottom here is called the trough. It looks kind of like a trough, you know, the things that pigs eat out of in old farm movies. How tall the wave is. So I guess I should back up. A wave is an oscillating, back and forth, movement between a highest point and a lowest point. So between this highest point and the lowest point, there is ground zero, if you will. And your distance above or below this ground zero is called your amplitude. So how big is it? How tall is it? Is it a kind of a flat wave or is it really tall? That's called the amplitude. The length of your wave, so from crest to crest, is called the wave length. Go figure. And the wave length can be measured from crest to crest, as is typical. We could also go from trough to trough. We could go from midpoint to midpoint. It really doesn't matter. All three of these are wavelengths. Wavelength is usually represented by the symbol lambda. It is a Greek letter. Is it lambda or lambda? Lambda. No, that doesn't look right. I don't speak Greek, sorry. If it were Japanese, I'd be in better shape. But anyway, this wavelength is one of the functions we're going to be looking at as far as effects the wave can have. How often or how quickly the wave goes up and down. So in this picture here, I've got from down to up to down, and then a half, so I would have 1.5 up and downs here. The number of up and downs is called frequency. And that should make some semblance of sense. You know, frequency, how often it goes up and down per second. And how often it goes up and down per second is usually indicative of the energy of a wave. So if we think about the wave as a means of conveying energy, that's actually what they are. If you think about an ocean wave, for example, if you are out in the middle of the ocean and the wave kind of comes rolling up and under you and then passes onwards, it is the energy that is being transferred, not matter itself, which seems a little counterintuitive, but it is true. So frequency, wavelength, and energy are all interlinked with the power of the wave. The best way to think about this is in terms of electromagnetic radiation, so things like visible light, color, as compared to something like an X-ray, which can see through your skin into your bones, versus something like gamma radiation, which can do serious damage. So how do we decide wavelength, frequency, energy? What is this relationship? So first let's talk about a wave like this guy. This guy has a really high frequency. It goes up and down an awful lot. So my frequency is high. High frequency. Lots of goings on. Really, really fast. Jitter, 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 jitter. My wavelength, as compared to this guy up here, if we look at this wavelength, from crest to crest, that's a really small wavelength. So as my frequency goes up, my wavelength goes down. And again, that should make some semblance of sense. If you take a slinky and you try to make waves with a slinky, if you want more waves, you've got to move it smaller, up and down and up and down and up and down. You're not going to be able to get these huge gargantuan waves and have a high frequency. It doesn't work. waves like this that have a high frequency and a low wavelength, you will generally see a higher energy. And again, this should make sense. If you're trying to make a lot of waves in the slinky, you have to exert a lot of effort to get that slinky to go up and down, up and down, up and down, up and down really fast. To qualify this a little bit, again, if you're thinking about something like radio waves are long waves. I'm talking a wavelength of kilometers. So that's a big wave. And radio waves are around you all the time. They have a huge wavelength, a very low frequency, and thus a very low energy, which means when they run into you, when you're listening to your radio in the car, it doesn't do you any damage. They're too big. They can't interact with your cells or your body. Again, we're talking wavelengths on the order of cars and buildings. It's too big. So that would be something like this wave here. This wave has a very high wavelength and a very low frequency. High wavelength, low frequency generally means lower energy. Again, think of your radio. Something like this, the smaller the wavelength gets, the more it is able to interact with you and your body on a cellular level, maybe even smaller. For example, UV radiation, ultraviolet radiation, thing that gives you a sunburn and potentially skin cancer. The whole reason it can give you skin cancer is because the ultraviolet wave has a small enough wavelength that it can actually interact with your body on a cellular level. The waves are small enough that they bump into cells, not big overarching skin thing. This is why it's easier to prick yourself with a pin than it is with a 2x4, because it's able to interact with your body on a smaller scale. Same thing with ultraviolet radiation. Because that wavelength is so small, the small wavelength allows it to interact with you on a smaller scale. That high frequency means high energy, and when it runs into you, that energy's got to go somewhere, and so it goes into your cells and does damage. The smaller the wavelength, the more damage it can do, because after ultraviolet radiation comes X-rays. X-rays are even smaller than ultraviolet radiation, so again, they can do more damage. This is why lots of X-rays is bad for your health. This is why when we get to something like gamma radiation, which has a wavelength about the size of an atom, maybe even smaller, so that tiny wavelength can actually interact with your body on a molecular level, and that tiny wavelength means huge frequencies and enormous energies. This is why nuclear explosions, nuclear weaponry, anything nuclear is so scary, is because of that gamma radiation. Nothing can stop it, because it interacts with things on a molecular level. Even feet of lead and concrete don't completely stop it. The last example that I have for you, you'll notice it looks very similar to, as far as wavelength and frequency goes, it looks very much like this one here. The only difference is the amplitude, and this is what I wanted to point out. Amplitude does not affect your frequency or your wavelength. Oh, one thing I did not mention. Symbols for frequencies that you see in equations, you see two different ones. If you're in chemistry, you see what looks like a V. It's actually the Greek letter nu. If you're in physics, you see the scripty looking F. But either way, both are frequency. Sorry. But anyway, amplitude is not going to affect your wavelength or your frequency. It just affects, for sound, it affects how loud the sound is. So please do not let amplitude affect any relationship you're looking at between energy, wavelength, and frequency. So I hope that gives you a brief introduction to the wave. There are other videos on my list that pertain to wave equations, some calculations with the wave, but this was meant to be just an introduction. So best of luck.